This is the prelab for the experiment entitled Rearrangement in the Conversion of Alcohols to Alkyl Halides. Both alcohols and alkyl halides are important functional groups due to their versatility as starting material, being able to transform into numerous other functional groups. In this experiment, we will look at the transformation of alcohols to alkyl halides and how the structure of the alcohol can determine potential rearrangement when forming the alkyl halide. In this video, we will cover the pre-lab assignment, safety information, the goals and the methods used to achieve those goals, information about the different classifications of alcohols and their ability to form carbocations, some specific information about conducting the experiment, how to clean up, and finally some tips on the PostLab analysis. Your assignment for this experiment consists of reading the assigned sections from the Techniques in Organic Chemistry and watching the demonstration video on the reflux apparatus found on the W.H. Freeman website under Williamson Movies. Since refluxing is a new technique you will encounter in this experiment, this video will show you how to assemble the reflux apparatus. Lastly, you will prepare your notebook using the preparative format, making sure that you use only your assigned alcohol. There are two distinct procedures for this experiment. Those of you who have been assigned 1-propanol or 2-pentanol will use the same procedure. However, those of you who have been assigned 2,4-dimethyl-3-pentanol will use a different procedure. The safety information you need to know for this experiment is divided into the two different procedures. For the reactions of 1-propanol and 2-pentanol, you will be reacting your assigned alcohol with sodium bromide in the presence of sulfuric acid. Sulfuric acid is corrosive and irritating. Because of this, you will want to protect your eyes, skin, and clothes. It also reacts with sodium bromide, producing hydrogen bromide gas, which is irritating as well. It is essential then that you cool your reaction mixture in an ice bath after completing the reflux time. You also want to avoid inhaling any vapors. The alcohols and alkyl halides are irritating and flammable, so do not use near open flame and avoid inhaling and ingesting any of the compounds. For the reaction of 2,4-dimethyl-3-pentanol, you react the alcohol with a Lucas reagent, which is a mixture of zinc chloride and hydrochloric acid. The Lucas reagent is highly corrosive and emits hydrogen chloride gas, so avoid inhaling and protect your eyes, skin, and clothes. You will also want to treat the alcohol and alkyl halide in a manner similar to the one previously mentioned in the other procedure. The main goal of this experiment is to determine the extent of rearrangement in 3 substitution reactions, one of 1-propanol, one of 2-pentanol, and one of 2,4-dimethyl-3-pentanol. To do this, you will each carry out the conversion of one of the alcohols to an alkyl halide. You will then determine your product by taking a carbon-13 NMR and observing the number of signals that arise. This will indicate the product or products that formed, due to the fact that different alkyl halides yield a different number of signals. Lastly, you will use class data to determine the relationship between alcohol structure and the extent of rearrangement. In lecture, you learned that alcohols react with hydrogen halides and undergo a nucleophilic substitution reaction. In this process, the rate of the reaction varies depending on the classification of the alcohol. In other words, whether the alcohol is primary, secondary, or tertiary. It's discovered that tertiary alcohols rapidly undergo substitution via an SN1 mechanism. A classical example of this is the reaction of tert-butyl alcohol with hydrogen bromide, where upon protonation, the tert-butyl oxonium ion will dissociate to form water and the tert-butyl carbocation. The nucleophile, in this case a bromide ion, then rapidly attacks the carbocation, yielding the alkyl bromide. Primary alcohols react very slowly with hydrogen halides. However, because the formation of a primary carbocation is energetically unfavorable, the reaction pathway follows an SN2 mechanism. In the example shown, the butyl oxonium ion cannot form a carbocation, so instead, the bromide attacks the carbon as water dissociates in a concerted mechanism, still forming the alkyl bromide as the end product. Secondary alcohols can form reasonably stable carbocations and tend to undergo substitution in a manner analogous to tertiary alcohols via an SN1 mechanism. However, the alkyl halides that form show evidence of carbocation rearrangement, and the extent of this rearrangement is determined by thermodynamics. If the carbocation can rearrange to a tertiary carbocation, then it does so in a rapid, almost irreversible manner. Rearrangement to another secondary carbocation can also happen at times. Because there isn't a significant difference in energy, this results in an equilibrium mixture of carbocations, which ends up resulting in a mixture of alkyl halides as products. We will probe these mechanistic possibilities by carrying out the reaction of a primary alcohol and two secondary alcohols, one where the carbocation formed can rearrange to a tertiary carbocation, and the other where a carbocation can rearrange to another secondary carbocation. The experiment consists of two different procedures, as was stated previously. For reactions of 1-propanol and 2-pentanol, the procedure requires you to reflux your sample. You are told to reflux for 20 minutes. Make sure you allow the reaction mixture to heat up and begin refluxing. You will see liquid condensing at the bottom of your condenser. Once you see this, then let the reaction go for the allotted 20 minutes. At the end, it is imperative that you cool the reaction mixture to minimize hydrogen bromide vapors. After the reaction has cooled, you are then going to set up a simple distillation. You know the distillation is complete when you see water coming over. And the last part of the procedure involves a separation and washing of your organic layer. Make sure you know which layer is the alkyl bromide. To do this, you can either look up the density of the alkyl bromide or test by adding a few drops of either layer to water to test its solubility. Also understand that when you distill, some sulfuric acid may azeotropically distill with your sample. To ensure neutralization of any acid, you will wash with an aqueous solution of sodium bicarbonate. This produces carbon dioxide gas, so make sure you vent a lot when working up the reaction in the separatory funnel. For the reaction of 2,4-dimethyl-3-pentanol, the first thing you will want to do is set up a 50-degree water bath. Your instructor will provide you information on the best way to do this. It takes some time to equilibrate, which is why you should do this first. Also, when washing the product, you will want to know where your alkyl chloride is by finding out its density or testing solubility in water. To clean up, simply place the product in the appropriate waste container, discard aqueous waste down the drain, and wash your glassware with water and detergent. For the PostLab Analysis section, you will need to exchange data with two students who have different alcohols. The only information you need to gather is finding out how many signals they have in their NMR spectra. And finally, one tip when drawing mechanisms. For 2,4-dimethyl-3-pentanol, hydrochloric acid is used in the presence of zinc chloride. The zinc chloride is a Lewis acid that increases the rate of the reaction. But when drawing the mechanism of this reaction, you're going to simply ignore the presence of the zinc chloride and treat 2,4-dimethyl-3-pentanol with hydrochloric acid, just like you've been shown in class.